Let's start with a very schematic picture of line broadening. If the crystal is perfect and large, then the peak in reciprocal space will be just a dot. You see that image when you do electron microscopy, transmission electron microscopy, and you switch to diffraction. Then you see sharp dots. And the same would be if you could do that in X-ray diffraction, which you cannot. Now, if you reduce the crystal size, then you see something like that, or you should see something like that, that each peak is blown up, and the blow up is uniform in reciprocal space. Of course, it becomes anisotropic if your scattering objects are very exotic. For example, if you have needles, or if you have chapatis. In my country, I would say pancakes, but here I can say chapati, which is much better. Then, of course, you can imagine that across the chapati, the size is very small. So if your diffraction vector goes through the chapati, then you will get a large broadening. But if it goes along the size of the chapati, then you have no line broadening. And that will make your blow up anisotropic. But globally, it will still remain homogeneous. That means that the higher order harmonics will have exactly the same broadening. You understand? For example, if you have this chapati and across the diffraction vector goes across the chapati, you have a large broadening, and let's say this is the 100 reflection and the 100 direction, then the 200, the 300, the 400, all will have exactly the same breadth. Is that clear? So in that sense, it remains homogeneous in the global sense. Now, your scattering objects have to be very odd-shaped to see this anisotropy. You can see this anisotropy. There is a classical paper, a beautiful classical paper from the 70s. I can give you the reference on zinc oxide. Zinc oxide can be grown as nanoparticles which are very long. Perhaps you know that. And these guys, Langford, Luer, and Odebram, Langford, I must say late Langford, I knew him very well. He was a very nice colleague in Birmingham, and Luer and Odebram are in France. They have been working a lot on the effect of size broadening. And this beautiful paper shows you that this nanocrystalline zinc oxide, which today is a hot topic because nanocrystalline zinc oxide is piezoelectric and all sorts of very crazy properties. They have shown this shape, the so-called shape anisotropy. There's a beautiful paper, very instructive to read. So if you can find it in Journal of Applied Crystallography, Langford, Luer, Odebran. Perhaps the first author is Odebran because she was the PhD student. So it is homogeneous, does not depend on the order of reflection, and becomes only weird if the shape is very exotic. However, if you introduce microstrain, practically you introduce dislocations, then the situation changes. Strain is making the peak not broad, is not affecting the breadth at the origin of reciprocal space, and its effect is continuously increasing as you go apart from the center. Okay? So that gives the hope and the chance to separate the two effects. This was recognized in the very early days because people were very smart always. Even the prehistoric man was very ingenious, but at that time Nobel laureate was not invented yet. It can be explained very easily that this must happen. You have seen yesterday many times that in diffraction, this factor E over I k r is the fundamental quantity, where k is the reciprocal space vector and r is the position vector in the crystal. Now, if the crystal is perfect, each atom sits exactly at its ideal position, then r is the ideal atom position. If, however, you have strain, then the atoms are removed from their ideal position in very different ways. Okay? And then r can be written as r plus u, okay? Where u is a displacement. Now, if you put this into that, and then you get E over I k times r plus u, which is again E over I k r times E over I k u. Now, this part is just the Fourier transform of your perfect crystal into reciprocal space. So this gives you the exact Bragg positions, the first term. Okay? Because if your crystal is perfect, then within the kinematical scattering theory, you have infinitely sharp peaks in each Bragg position. That is actually one of the faults in kinematical scattering theory. But we don't care about that. What about this? When k, that means the reciprocal space, called u is small. U is small, smaller than r. Okay? The displacement cannot be large, because if the displacement would be large, and especially random, what would be the crystal? Amorphous. We are not caring about amorphous materials when we do line profile analysis. We should, but that is more complicated. So u is much smaller than r. So this is a very small number. When k is 0, okay, that is the origin of reciprocal space, what is this quantity? Is unity. No effect of strain. Okay? So it is so simple. And as k increases, this second factor is increasing the effect of strain. That is what we see in this schematic graph. And finally, if we have planar defects, then we have streaking. Now, streaking you have seen, or you can see in the TEM. If you have twins or stacking folds and you make an electron diffraction image, if you do electron diffraction, you can see that the spots are connected with very faint thin lines, which is called streaking. In X-ray diffraction, you don't see the streaks, but you see peak broadening, because the streaks are projected. If I come to that, I will show you how this happens. I have to come to one point here. There can be two different approaches to line profile analysis. One can be called top-down, the other one can be called bottom-up. Top-down means, well, that is a fantasy. You can, in principle, think that you have a diffraction pattern and you describe the peak profiles by well-known profile functions. And then you try to interpret the different profile function fractions in terms of some microstructure features. In the bottom-up approach, you start from the bottom, and that is the TEM micrograph. You look into it, and you see that you have dislocations, you have, well, you don't see the vacancies, and you don't see the internal stresses. In a TEM, you don't see the internal stresses. There are methods which people try, for example, convergent beam electron diffraction, but it has gone out of fashion. Nowadays, nobody is applying it because it is so complicated and actually not very precise. So there are much better other methods. So for internal stresses, TEM is not very good. This I can say for sure. You see twin boundaries, you see stacking folds, you see partial dislocations, you see full dislocations. So now you start working to develop profile functions from scratch to build up from the displacement field created by the lattice defect. Okay, that is bottom up. And this was first done by the late Krivoglass. I have to write down his name because his contribution is so important. He worked in the Ukraine and he was a theoretician. And he has written a book, a thick book, neutron, and I think X-ray and neutron diffraction of distorted crystals. That is the title of the book. It was translated into English. The original was in Russian. It was translated to English and it was published by Springer. You can buy it or you can download it. I don't think it is legal, but you can do it. You didn't hear it from me. To read the book is not easy. It is rather confusing, the book itself. It is a very severe study to go through all the details of the book. But he realized that the major the most important part in a diffraction peak is the tail region, and that is most sensitive to dislocations. The size effect, I must say, is not so complicated because it is an optical effect. We learned that in school, that if an electromagnetic beam, light, is going through a slit, it is diffracted, and the diffracted spot is blurred up or becomes sharp depending on the nature of the slit or the grid. That is a purely optical effect, and it is not so difficult to work it out. The effect of dislocations, that means the microstrain, is more difficult because the assumption which you can find in the book of Warren, well, Warren, the name of Warren must be also mentioned, because he has not only given a long chapter in his book, in his small book, X-ray diffraction, a beautiful small book. I love it. I didn't grow up on the book of Quality, but I appreciate the book of Quality too, because I think that is also an excellent handbook. I don't think these two books could be surmounted today. They are so ingenious, both of them. So Warren was working very much, well, Warren has many topics, has made contribution to many fields which are valid today. For example, the Warren-Cawley order parameters, that is something fantastic. That is all treated in his book. Thermal diffuse scattering is also treated in his book. Beautiful chapters. Line broadening is a thick chapter, and also there is an even more detailed paper, actually, review paper, in the series of Progress in Metal Physics. It was, I think, published in 1956 or 58. It is practically the same as in the book. And he made the assumption for strain broadening that the atoms are removed randomly. And this is a fundamentally wrong assumption. Very sorry for Mr. Warren, but this has to be said. The displacements caused by dislocations are far from being random. They are absolutely correlated. Okay? Because a dislocation is an object. It is the edge of the extra plane, and the displacement field can be calculated exactly. So it is absolutely correlated. Nothing like uncorrelated. If the displacements would be uncorrelated, random, the material would be amorphous. But even in the amorphous material, the displacements or the atomic positions are not absolutely random. There is a short-range order, which Cawley himself worked out. So in his approach, this assumption is wrong. All the rest is fine. The mathematics is fine, though I would prefer another one, because Warren is working by sums. He is writing summations. He must have been a terrific mathematician, but to read mathematical derivations based on sums is a little bit cumbersome. So integrals are more friendly, user-friendly. And in the Krivoglass book, you have only integrals. Krivoglass was a PhD student of Landau. You must have heard of Landau. And Landau was the master of statistical physics. And Landau, of course, learned statistics or statistical physics from his master Landau. And he realized that a single dislocation is not a dislocation. And that was the mistake in many papers of Wilson. I don't know, maybe you have not come across that name, doesn't matter. There is a thick book on X-ray diffraction, A.G.C. Wilson, and he worked a lot on the effect of line profiles produced by single dislocations. A single dislocation does not do anything. It is not a dislocation. Dislocations are always a manifold. You have to treat them by statistical mechanical methods as a manifold, as an agglomerate. And that was the first, Krivoglass was the first who realized that and described the effect of many dislocations on a line profile. Okay, his profile function was partly good, and I will show you how it was improved by the late Wilkens. Okay, so the bottom up means that you go down to the objects, which on the one hand are the dislocations. They are the coherently scattering domains, which in more realistic terms are either the grain size or the subgrain size. If your grain size is 100 micron and you still have a size effect, then it cannot be the grain size, what you see, but it can only be the subgrain size. If your grain size is 50 nanometer, which today is absolutely common sense, then your grain size, what you see, is identical with what you see in the TM. That is unfortunately an ambiguity in the size effect by X-rays. You have to know what your material is. You have to know something about your material to understand the diffraction pattern. So the profile function has to be worked out for dislocations, for planar defects, separately for twins, for stacking faults in different materials, in cubic materials, in hexagonal materials. The twinning is much more complicated. In the structural materials like magnesium, zirconium, beryllium, or titanium, you have the pyramidal planes which twin. It is a research topic for itself to work out the line profile effect of these crazy twinning planes, but it can be done. And then you can put together your diffraction pattern with these theoretically calculated profile functions, which have nothing to do with the mathematical profile functions, but are ab initio calculated profile functions, but they contain parameters which from the beginning have physical meaning. These are, I come back for a moment to the top-down method, okay? These are the analytical functions which are used in what? In the Rietveld method, okay? The easiest is the pseudo-Voigt, okay? The pseudo-Voigtian. Actually, originally it was the Voigtian function, but before laptops or PCs, integration was too difficult, so people invented the pseudo-Voigt instead of the Voigt, in which the Gaussian and the Lorentzian are not convoluted, but just added up with a fraction. That is the difference between Voitian and pseudo-Voitian. Pseudo-Voitian works perfectly for Rietveld. Please try to remember that Rietveld, the Rietveld method, is a great procedure to refine the crystal structure. It is a structure refinement method. Structure refinement. You are tuning the atomic position in the unit cell until your calculated and measured pattern fit each other. This is the quintessence of the idea of Rietveld. Line profile, at the end of a Rietveld, there is, I must say, the wrong concept to say that the Lorentzian fraction of a pseudo-Voitian function is the size effect and the Gaussian is the strain effect. I strongly object to that concept. And I'm not alone with that. There are many other groups which would agree with that concept, that this is not true. I will show you how much this is not true. So Rietveld is the best method for refining structure. Line profile analysis, which is not Rietveld, is the best method to characterize the microstructure. Yeah, so for many good reasons, I would like to turn to the bottom up. I told you this. Before we go on, let me show you the concept of the hierarchy of non-size type lattice defects. Size type is the grain size or the subgrain size, or twins or stacking folds. Why twins or stacking folds? It has a very simple reason. If this is a grain and there is a twin boundary, then if you look from that direction, then you see this as the size, okay? Because the twin boundary or the stacking fold will divide the crystal into two perfect crystals. If you look from that side, then the size will be this. Okay, it is so simple. So it is a kind of complicated size effect. Now, so let's see the non-size type lattice defects. You can, just for dimensionality, you can categorize them, you can imagine, into three types. Zero dimension are the point defects, or point defect like a small precipitates. Okay? Our planet, we wouldn't say that our planet is a point, because we cannot live on a point. But if we go to the other end of the galaxy, then our planet is a point. So a small precipitate or a precipitate or an inclusion, if you go far enough, is a point. If you are very close to it, you see the surface. So it is a plane. Okay? But the strain is decaying fast. This is a fast decay, 1 over r square. Okay? That can be integrated. 1 over r square can be integrated, and it will give you a finite result. One dimension is the next. One-dimensional, the profound example of a one-dimensional effect, lattice defect, is a dislocation because it is a line. its strain field, if you go to any textbook, you can convince yourself, its strain field is 1 over r. 1 over r is long range. It cannot be integrated. Okay? Long range. The other one is short range. And two-dimensional, I don't know if you can see the bottom. Can you see the bottom? It says the strain is constant. Okay? A large flat surface, the strain, if you don't go very far, the strain doesn't change. The strain is constant. So what is the effect? Crystal space, we were talking about yesterday, I was not talking about, but you heard so much about that yesterday. You have crystal space, you have reciprocal space. Diffraction is in reciprocal space. Actually, I always want to say that the reciprocal space is only in our head. It doesn't exist. But it is good to know the reciprocal space because you can think much easier. A short distance in crystal space will be a long distance in reciprocal. This was discussed yesterday in detail. Remember? And vice versa. A long distance in crystal space will be a short distance in reciprocal space. That is just because of dimensionality. One is measured in meters, the other one is measured in reciprocal meters. The zero-dimensional defect, vacancies, interstitials, small precipitates, the strain field is reaching to short distances because it is short range. So in diffraction, they will give you diffraction at large distances from the Bragg reflection. I don't know if this is clear. Is that clear? So you get lousy, slowly varying, background-like diffraction below the Bragg peaks. Today there is a book on that topic. The title is Total Diffraction. No, the topic is total diffraction, but the title of the book, it is written by Egami and another guy. It is Beneath or Below the Bragg Reflections. That is the title. And the concept is that if you have nanocrystals or nanocrystalline materials, then below the Bragg reflections you have diffuse scattering, and the idea is to evaluate the Bragg peaks and the diffuse pattern together. That is total diffraction. We are not doing that. It is a difficult subject. So I'm showing you here a diffraction pattern which was cut off. The top of the diffraction peaks is cut off, but they reach up 100 times more than what you see here. So this is the bottom part of the diffraction pattern. And I will show you in the next slide the total diffraction pattern, where the red almost disappears as a straight line. This diffuse scattering in the literature is also called Huang scattering. It's just a name. Dislocations in crystal space have long-range strain field. Okay? So in reciprocal space, the scattering will concentrate to the Bragg position, and that is line broadening. And that is why it is small. Okay? So now the red is what the dislocations do, and what we have seen before, this diffuse scattering in the bottom, is now hardly seen. because the intensity goes up to 3000 instead of 40. So the difference is almost 100. And if you have twinning, you can see the peak shift. Okay? And peak shift means constant strain. Okay? This was nanocrystalline nickel iron measured at synchrotron. Well, you can do the measurement in the home laboratory. But here, in these measurements, the diffuse scattering was also very clearly seen because the intensity was so good. So, 0 dimension, you have precipitates, inclusions, point defects. 1 dimension, dislocations or dislocation type defects, linear defects, okay, 1-dimensional linear defects, whose strain field is very similar to the strain field of real dislocations. If you can have what is a not real dislocation, if you have a polycrystal, you must have heard of the triple junction. Yes. 3 grains meet and a line, or disclinations. They are also dislocation type defects. Dislocations is a complicated thing. I don't know yet the exact effect of disclinations on line broadening, the direct effect, but I'm working on that with a colleague together. 2-dimensional, these are the planar defects, stacking faults, twin boundaries, grain boundaries, domain boundaries. Strain is constant. I encircled this because when you see line broadening, then the non-size type effect must come from a linear defect, from a 1-dimensional linear defect, whatever it is. It can be a sinter stress. If 2 particles touch each other, in powder metallurgy, you press the particles together. They are pressed in on the touching surface, and the boundary of the touching surface is a line, and that is a linear defect. So the sinter stress, this is known in powder metallurgy, this term, is also producing line broadening of a similar type as dislocations. So we can say that line broadening is caused by strain if and only if the strain is produced by linear type defects. The prototype of linear type defects is dislocations. We could say that this is the dislocation theorem of strain broadening. Now, I already mentioned the name of Warren because his work was very crucial. His book in 1958. Yeah.
This statement is not clear. The line broadening is caused by strain if and only if the strain is produced by linear type.
Yes, so strain effect in line broadening must have linear type defects in the crystal. I don't know if it is clear in that. Perhaps the formulation is not clear. I want to say that...
In the previous slide you showed that all of them are causing a strain, which are varying differently.
Yes.
As R square and constant.
Yes.
Yeah.
Yes. But line broadening, I'm saying that line broadening, you see, because point defects produce a Houang scattering, planar defects make a shift, and also a broadening because the streaks are projected. That is actually not a strain effect. I can come back to that if we have time to talk about planar defects. Okay? So the effect of planar defects is apparently similar to dislocations, but it can be shown that it is not. It is not monotonously increasing as you go apart from the origin of reciprocal space, but it will stay the same for the higher order harmonics. The line broadening remains the same for planar defects. Okay, so that is the difference between true strain broadening and other line broadening causes. I don't know if perhaps it could be reformulated. Do you have a suggestion?
Well, maybe we will discuss that.
Okay. But I don't know if it is clear now that strain broadening of line profiles, not the diffuse scattering and not the peak shift, must have something behind it which is linear, a defect which is linear. Okay? Now, if you go to the Bohren book, you will find that peaks can be Fourier transformed. Yesterday, I think there was something about that. And the Fourier coefficient of G is the diffraction vector. Okay, so HKL is in G. L is the Fourier variable. Okay, so L is measured in meter. G is measured in reciprocal meter. And you have two Fourier coefficients, one for the size effect, S is for the size, and one for the strain effect. And the quintessence of the strain is summarized in this quantity, which we call mean square strain. I have prepared a separate presentation, a short one, about the mean square strain, and perhaps we can go through that also the other day. The only physical quantity here is the mean square strain, because L is the Fourier variable and G is the diffraction vector. Okay? So it is so simple. And now we have to say what is the correlation between the mean square strain and the lattice defects. Okay? Only the strain type lattice defects, because the size is extracted in terms of a separate Fourier coefficient. Okay? Now, well, this is the strain Fourier coefficient. Okay, this exponential. Now, I write down immediately the end of the story, which is here, that the mean square strain, this quantity, is not only a function of HKL, but also a function of the Fourier variable. And it can be written in this apparently simple form. That is the result of Wilkens, of Krivoglass and Wilkens, both. Now, in this expression, we'll go, in a separate presentation, we can go a bit into details. Rho stands for the dislocation density. More dislocations, you will have more mean square strain, more line broadening, strain broadening. Burgers vector, if the Burgers vector of a dislocation is larger, then the atomic displacements will be larger. Okay? It is proportional to the square of the Burgers vector. This quantity, f eta, this is a function which describes the L dependence of the mean square strain, where, I don't know if you can see that, I write it down here. Unfortunately, bottom is a little bit hidden. And this is very important. Ask questions freely. So eta is L over Re, where L is the Fourier variable and Re is the so-called effective outer cutoff radius of dislocations. In the Krivoglass formula, which Krivoglass derived, and you also find it in his book, instead of this f eta, there is a logarithmic term. There is a logarithmic term. So Krivoglass says that instead of this f eta, he says ln d over b. D is, I think not even that, but d over L. D over L. D over L. This is the Krivoglass formula, where D is the size of the crystal. Okay, D, I don't shine this pointer to the green board, to the blackboard, because it reflects, and that is dangerous. But you can see ln d over L, where d is the crystal size. Now, there is a problem with that. If you have a constant dislocation density, okay, your dislocation density is constant, and you start increasing the crystal size, what will happen to this logarithmic term? If you increase your crystal size to infinite, what will happen to that logarithmic term? No, the d, you are increasing the d value to infinity. What will happen to that logarithmic term with a constant dislocation density? You have a single crystal infinitely large with a constant dislocation density, and you start increasing the d value to infinity. What? It goes to infinity. Yeah. So this formula cannot be true because it has this logarithmic singularity. Okay? It's logarithmic singularity.
Size of the crystal is fixed, right?
No, I'm saying that theoretically, if you would write, if you write the Krivoglass formula, looks like that: epsilon square average equals rho c b square over 4 pi ln d over L. That you find in the book of Krivoglass. Okay? And Krivoglass says that d is the size of the crystal. Now, if you start with a crystal that size and you have dislocations, but you have the same dislocation density everywhere, and you start increasing the size, then what is doing that? You have everywhere the same density. Then the mean square strain is doing what? Pardon? Is increasing, okay? Which is physically a nonsense. Well, we shouldn't say nonsense because Krivoglass was a very smart guy. But now, if you go to your textbook on plastic deformation, you also have a formula which tells you the stored energy, the elastically stored energy of dislocations. Okay? How does this look like? There is a constant which depends on if it is screw or edge dislocation. Did anybody see that formula in the textbooks? The elastic stored energy of dislocations. It is part of the plasticity lecture. A, G is the shear modulus, B, square root rho, no, B square rho ln, there is a logarithmic term, okay? What is in the logarithmic term? You can put here D over B. This is what you can put in, but this is again wrong. B is the Burgers factor because it is a continuum mechanical formula and you cannot go closer by continuum mechanics than the atomic distance. That has no sense. Otherwise you get a singularity at short distances. Now what about the size of your crystal? If you increase the size of the crystal, the elastic stored energy is again logarithmically singular, okay? Although the dislocation density is a constant. Now how was this problem solved? Independent of line profile analysis, just in mechanics, in dislocation theory. How was this solved? By introducing the effective outer cutoff radius. So you have two cutoff radii. B is the inner cutoff radius, and here you introduce RE, which is the outer cutoff radius. You must introduce that. That means that the dislocations are not distributed randomly, not perfectly randomly, but they are screening the strain field of each other. There is a certain distance beyond which the strain field of a particular dislocation does not reach out. It is screened perfectly by the surrounding dislocations. Okay? It must be like that. It is the renormalization of this logarithmic singularity. And Wilkens has realized that the same must be done for the mean square strain. So he introduced the effective outer cutoff radius in the same manner as it is done in the stored energy. Okay? You can read two papers in Acta Materialia or Acta Metallurgica, because it was published in 1967, two consecutive papers, one after the other. Scattergood and Cox, these two guys have never dealt with line profile analysis. And the other paper is Wilkens. Two papers, one after the other, in Acta Metallurgica. 1967. In the first one, you have the concept of effective outer cutoff radius in the stored energy. And in the second paper, you have the concept of outer cutoff radius in the mean square strain. And both discover that the dislocation ensemble is never perfectly random. In the Krivoglass approach, it was said that they are perfectly random. If they are perfectly random, then the effective outer cutoff radius is infinite. But if there is a screening effect, then it is finite. Okay. And Wilkens, yeah?
So you talked about the outer cutoff radius.
Yes.
Inner cutoff radius we have taken as the Burgers vector.
Yes.
But there is also something known as the radius of the core of the dislocation.
Yeah.
So is there a way we can get some idea, because there are quite a few interesting things happening in the core of the dislocation. Like people talk about core splitting and other things. So can we use X-ray diffraction to get some idea about that?
I don't think so. At least, well, you should never say no. Because then somebody comes and discovers that it can be done, and then you were wrong. So I should not say no. I don't know. But if this is one peak, and this is another peak, the core effect is seen halfway between the two. How can you measure this intensity? Halfway between the two. Okay? That is where the core is. Okay? Halfway between two Bragg reflections. You would have to measure what is here. You could do it, well, in principle you can do it, but I don't think, well, today I think practically it would be difficult. Okay, so the further you go away from the Bragg peak, the closer you go to the dislocation. And you are at the core when you are halfway between two Bragg reflections. That is just the idea of reciprocal space. Yeah? Okay. Yeah. So this is the, okay. Now, coming back here. Look, if you want to have the whole strain profile, this is the Fourier coefficient of the strain profile. Okay, this exponential, very simple function. The mean square strain has to be known for the entire Fourier range, because the inverse Fourier transform will give you the strain profile. Okay? And that is what Wilkens has done beyond introducing the effective outer cutoff radius. He calculated numerically how the mean square strain depends on L, the Fourier variable, in the entire range. So then you have a chance to inverse Fourier transform this simple expression, because you put in the exact formula for the mean square strain. You can do the inverse Fourier transform, and you have the strain profile. So this is the function of Wilkens, and it has two parts. The first part here, this is the logarithmic part, which was calculated by Krivoglass correctly. Okay? But of course, together with the, if you replace d with the effective outer cutoff radius, then this is the logarithmic part. So Krivoglass was correct as far as the logarithmic is concerned. Only you have to replace the crystal size by the cutoff radius, outer cutoff radius. Now the problem with the logarithmic term is that it goes down to negative values. Look, the double dot dash is the logarithmic formula, but the mean square strain cannot be negative. So Wilkens took the pain, calculated this mean square strain by a simple dislocation model. He took straight, parallel, screw dislocations. Today, there is a lot of critical comment in the literature that whether this can be used, straight, parallel, screw dislocations. Well, you have to remember that was done in 1967, 1970. So now, how much? More than 40 years ago. He didn't have a PC. He didn't have a laptop. He had a small programmable computer. You could write small programs on little magnetic tapes, put it in, and do numerical calculations. That is how he was working. But nobody could do a better job today, until today. So he showed that the asymptotic function at large eta values, eta is the Fourier variable normalized with the outer cutoff radius, okay? L over RE. And he has shown that this is a hyperbola, 1 over eta, and he matched the two functions together just by brute force and produced this blue curve, which is working very well. It is working, okay? And it contains the outer cutoff radius. So if we go back to that formula, we have the dislocation density, the number density of dislocations here. It is a proportionality factor. And we have the effective outer cutoff radius here. So both quantities are in this formula. Okay? Now, this is a random distribution of 10 dislocations. If you calculate them, 2, 4, 6, 8, 10, they are 12. And here are 1, 2, 3, 4, 5, 6, also 12. Two very different arrangements. The strain field of the two arrangements must be different. Okay? In the left-hand side, you expect a large strain. In the right-hand side, these are highly correlated. Sometimes we can call that small angular grain boundary. What do you think the strain field is? That here the strain field is very strongly screened. Some people say that a small angular grain boundary has no strain effect, which is not true. Because if you go close enough to the dislocation, that means you go far enough from the Bragg peak, you see only one dislocation. So why should it not have a strain effect? It does have strain, but it is very strongly screened. Okay? In the left-hand side, the effective outer cutoff radius is obviously larger than the average distance. You have an average distance of the dislocations, and the outer cutoff radius can be measured in terms of the average distance. Okay? We want to characterize the screening by a shear number which has no dimension. And that was introduced by Wilkens, this m. Now, the reciprocal average distance is the square root of the dislocation density. So if you make this quantity Re over d, that means this is dimensionless, then you end up with Re times square root rho, which is a number. And if this is larger than 1, for this dislocation arrangement, this will be larger than 1. This m parameter, the dislocation arrangement parameter, will be larger than 1. In the other case, it is the other way around. It will be much smaller. So how can we see that in the diffraction peaks? Can we see that effect in the diffraction peaks? Well, theoretically, of course we can. When m is very small, then we have this long tail. These are two calculated peaks. The intensity is normalized to 1, and the breadth is normalized to 1, normalized together. And if this arrangement parameter is very small, that means strong screening, then the tail is long. If it is small, if the m parameter, if the arrangement parameter is very large, that means the screening is weak, it is better to say that the dislocations have a dipole character or a weak dipole character. Then the tail is short. In the upper case, the profile function is similar, not exactly, but similar to a Lorentzian function. In the other case, it is not exactly, but similar to a Gaussian. So what about the Rietveld Gaussian and Lorentzian fraction of the profile function? It doesn't make sense. Okay? I hope you can, well, I'm trying to convince you that it is better to use this approach and leave Rietveld for the application for which it was invented. And there is no horse which can be used for everything. You cannot fly on a horse, only in a saga. But you can ride a horse, and you cannot ride an aeroplane. Well, this is a stupid parabola, but I just invented it. So I show you an experiment which was done by Wilkens, a PhD student called Hertz, and Mugrabi in 1980. It was published in Zeitschrift für Metallkunde. You see here 3 peaks. The upper one has long tails. The center one has short tails, and the lower one also has short tails. Unfortunately, I could not put them onto each other because I can only copy them as an image, and then they cannot be transparent. Otherwise, it would be nice to put them together. These are the corresponding TEM micrographs. The upper one corresponds to a cyclically deformed single crystal with persistent slip bands. Now, in the persistent slip bands, which is this ladder structure, you have dislocation walls in which the dislocations are hammered together to an extremely high dislocation density. All of them are edge dislocations in very strong dipole configuration. The screening is very strong. So you have long tails. Here, the amplitude of the fatigue experiment was small. With small amplitude, you get the persistent slip band structure, PSBs. Okay? If the amplitude in fatigue is large, then immediately you end up with a cell structure. that is shown here. And the cell walls are loose dislocation configurations where the dipole character is not so strong. Okay? So the tail becomes shorter. I don't know if you can see that in this curve the tail is long, whereas in this one it is short. You can see that. And the last one was a tensile deformed specimen, single crystal. And if you look carefully, you can see that this peak is asymmetric. Can you see that? At that time, these three colleagues did not care about this asymmetry. It was my privilege to join this group, and the first peaks with that strong asymmetry was done when I joined the group. So you might have seen that I was also one of the co-authors of those papers. But this asymmetry was there even before. That was published in 1980, just shortly before I arrived in Stuttgart in 1980, but then this paper was already out.
This
Okay.
long and short tail is not really obvious from the figure.
You need
Looks
you
more
need
or less
some
the same.
fantasy. No, look. This tail
Yeah.
is longer than this one. I can try to digitalize it and put them together. Can't you see that? Who can see it, that one is longer than the other one? Then the upper, here the tail is longer. It means it goes down at a slower rate than here. You see, this shape is somewhat, this peak is pointed upwards. It is like that. The other one is more bell-shaped with a shorter tail. Okay? So if we would put them together, then the difference would be, I'll show you that. One would be like that. The other one would be like that. Somewhat exaggerating, but this is the difference. Now,
Length of the tail should relate to where it's becoming zero, isn't it?
yes. Yeah. Not exactly, because you see here also where it becomes, it has to be normalized to the full width half max. Because we are only concerned about the shape, not the absolute values, only the shape. So they are crossing each other at the full width half maximum. They are crossing each other. Okay? I don't know, can you see it now? That the upper one is, if you would blow up that to the same full width half maximum as this one, then the tail would be definitely longer. Okay? This is the point. And physically, the physics behind that is also clear. If the dipoles are screening each other strongly, that means the strain goes down fast in the crystal. That means the diffraction goes very far from the Bragg peak. Okay? Whereas if the dislocations are just randomly scattered in the body, then the strain field goes very far and the diffraction is concentrated around the Bragg position. And it goes down, the intensity goes down faster. So the physics is clear.
But in this kind of intersection, the two have the same width, full width
Well,
at half maximum.
Yes,
But that may not be the case. No?
doesn't matter. We are only we only analyze the shape. We don't care about the breadth. Okay? Of course, you see, because in the we have two parameters for the dislocation structure. We have two parameters for the dislocation structure. Mean square strain is proportional to the number density, and it's proportional to, we can write the Krivoglass formula to ln Re over L. Okay? This is the major point. This will give you the peak shape in the tail region. Okay? So, the number density is one thing, but the screening is also important. If Re is very small, if the screening is strong, then to have the same breadth, you need more dislocations. Okay? If the screening is weak and Re is large, it can be an order of magnitude larger, then you need much smaller number of dislocations to give you the same breadth. So the breadth alone is not sufficient. Any questions regarding this? Or okay, later we can come back. So strain profile in cubic crystals can be given by three parameters: the dislocation density and the arrangement parameter, or the dipole character. And I didn't talk about one quantity, this C. There is a factor which gives you the correlation between the three vectors, because again, a dislocation has L line vector. If it is an H dislocation, it has a Burgers vector, and the diffraction experiment has a diffraction vector. And these three vectors can have any relation to each other. And that will result in a number which we can call the contrast factor, which is so well known in transmission electron microscopy. If you tilt your specimen, then a dislocation contrast can become strong or can disappear, and you can use this effect for Burgers vector analysis in a TEM. But X-rays are also a wave, so why not the same? There's no difference. Of course, there is difference because in TEM you see the individual dislocation, and with a diffraction experiment you shine a volume and you can only see an average of a volume. But otherwise, both waves are diffracted. Okay, the strain profile.
What you wrote C and on the screen it was Q. Is the same?
Yeah, that I went too fast. This C will be a function of Q. A parameter. I will come back to that later. Okay? I'm sorry.
What is M? Arrangement parameter?
M is the arrangement parameter. This, we said this is M is equal RE times square root rho. It's just a number between a few tenths and 5 or 10.
Most of the time, in a much more simplistic way, people they try to correlate with the strain actually to the dislocation density. I think that should not be the case. I think what you feel, I think it depends on how they are arranged actually.
Yes.
I think
Yeah.
yeah. Arrangement parameter has to.
Yeah.
Has to be considered.
Yeah.
But how much difference normally you see is like.
It depends on your structure.
It's like suppose that normally what they calculate now is like directly actually with some formula is like people they correlate with the strain and dislocation density, and if you don't consider the arrangement parameter, and that's what my point.
If you don't consider it, tacitly you do assume an arrangement parameter.
Because severely deformed material means like normally you will say it's like it's more or less random, rather than the mistake will arrange.
Yeah, if it is random, then your M parameter will be large. But it can be not random, then it goes down. It depends. But of course you have seen that it is in the tail region, so you need a measurement in which the tail can be evaluated. Okay. So the strain profile looks like that. Okay, it is the inverse Fourier transform of this simple formula where the mean square strain is given as all that blah blah which I was talking about. Here it is again. The size profile, we didn't talk about the size profile. Shall we still have 5 minutes, unless you wanted to ask questions, but we can discuss questions later. Well, for a monodisperse size, the formula is very simple. It is sine square something over sine square x divided by x square. You find this formula, you can calculate the shape factor for a sphere, very simple. But you always have a size distribution, and the logarithmic normal size distribution function is a very good function. It is written here, where you have a median, which gives you the position of the size distribution, and the variance, sigma, which gives you the width or the variance of the size distribution. And these can be incorporated in the size distribution, in the size profile, which then looks like that, where this is the the complementary error function. But you recognize that there is m in that formula and sigma in that formula, and this is the formula for a single sphere. That you find in the first pages of a textbook. So what you can do is you measure the diffraction pattern, then you have a calculated strain profile, a calculated size profile, and we didn't talk about the planar defects profiles, but that can also be calculated ab initio. You convolute these, you convolute them with the instrumental effect, and you add the background. So on the right hand side you have the diffraction pattern calculated in principle similar to what you do in a Rietveld method. So you don't touch the measurement, you calculate your pattern. The only difference to Rietveld is that in the Rietveld here you put a pseudo-void function. Okay? That is the only difference. Okay? And you match the two by a nonlinear least squares fitting, and the physical parameters for the strain profile are, we discussed that before, these three. For the size, we have these two, the median and the variance. And for planar defects, we have the frequency or the density of the planar defects. Recently, we have been working on the thorough update of the software. This has been put into a software called Convolutional Multiple Hole Profile, CMWP. Recently, we have been working on updating, but actually it is a perfectly new version, and as soon as the developing process is finished, we will release that, and you can download it, or I can send it to you. The problem with the nonlinear least squares fitting is that if you have too many parameters, then the parameter space will have many pockets, and the fitting can get stuck in one of the local minima. So we included a Monte Carlo procedure in which the physical parameters are evaluated by the Monte Carlo, and the peak positions and peak intensities are still worked out with the nonlinear least squares fitting. So there is a combination of Monte Carlo and nonlinear least squares to obtain the global minimum. And we have done a very, very good progress. I can show you how it works at this stage in one of the practical courses. And as soon as we finish the development, I can send you that version. It works exactly the same manner as the old one on a Linux platform, and it should be easier to work with it because it is not so sensitive to the initial values of the physical parameters. It finds the true parameters straightforwardly. So this is the old version. I don't know if you can see the green one. The red is the measured pattern. Blue is the background, which was done manually because we don't have a model for the background. And the green is the calculated pattern. Okay. Thank you for your kind attention.